Welcome back to the Deep Dive. We're continuing our journey through the Online Encyclopedia of Integer Sequences, the OEIS. It's just such a gold mine, especially if you're into number theory or combinatorics.
Absolutely. And today we've picked out a really interesting one to dig into. Sequence A000246.
Right. The OEIS description calls it the number of permutations in the symmetric group Sn that have odd order. Now, that sounds fairly simple on the surface.
But as we look through the source material, research papers, some background articles, even online math forums, it turns out there's, well, quite a bit packed into that definition, some really neat connections.
So our mission today is to unpack what odd order really means for this specific sequence, A000246, and explore some of the fascinating properties that popped out from the research.
Let's dive in. First off, Sn, the symmetric group.
That's just all the ways you can rearrange the numbers, one,
Yeah.
two, up there, right? The permutations.
Exactly. All possible shuffles. And a really fundamental tool for understanding any permutation is breaking it down into disjoint cycles.
Disjoint cycles. Like cycles that don't share any numbers.
Precisely. Any permutation can be uniquely written as a product of these non-overlapping cycles. The sources all emphasize this decomposition.
Okay, like if we're in S4, the permutation swapping 1 and 2 and swapping 3 and 4, that's 1, 2 times 3, 4. 2 disjoint cycles.
Perfect example. Now, the standard definition of the order of a permutation, this is basic group theory, is the least common multiple, the LCM, of the lengths of those disjoint cycles.
Right, so for your example, 1, 2, 3, 4, the lengths are 2 and 2, LCM 2, 2 is 2, so order 2.
Correct. Or, say, a single cycle like 1, 2, 3, 4, 5 in S5, length is 5, LCM of just 5 is 5, order 5.
Makes sense.
But, and this is the crucial point from the main research paper for A000246.
Ah, here's the twist.
Yes, this sequence, O000246, does not count permutations where the LCM of the cycle lengths is odd.
Wait, really? That seems like the natural interpretation of odd order.
It does, but the paper defines it differently. S000246 counts permutations where every single cycle in the disjoint decomposition has an odd length.
Every single one. Okay, so let's take that example. 1, 2, 3, 4, 5, 6 in S6. Cycle lengths are 3 and 3, both odd.
Correct. So that one is counted by A000246, and its LCM is 3, which happens to be odd.
Okay, what about 1, 2, 3, 4, 5 in S5? Lengths are 3 and 2.
See, there's an even length cycle, the 4, 5. So even though the length 3 cycle is odd...
It doesn't count because not all cycles are odd length.
Exactly. It's not counted by A000246, and its LCM 32 is 6, which is even anyway.
Got it. So the definition for this sequence is super specific. All cycle lengths must be odd. That's what odd order means here.
Precisely. The paper is very clear, whose every cycle is of odd length. That's the rule for A000246.
Okay, good to clarify. Now, another point of confusion that came up in the discussions we looked at, the difference between odd order, as we've just defined it, and odd parity.
Right, parity or signature. That's about whether you can get the permutation by an even or odd number of two-element swaps, called transpositions.
Yeah, the even and odd permutations. Even ones have signature plus 1, odd ones have minus 1. You can figure it out from inversions or the cycles too, right?
Yes, and the cycle method is relevant here. The parity of a single cycle of length L is given by -1 to the power of L1.
Which is the part that always feels backwards.
It really does. So if a cycle has odd length, say L3, then L1 equals 2, and -1, 2 is +1.
So an odd length cycle has even parity, plus 1.
Correct. And if a cycle has even length, say L2, L1 is ln of 1, and -1, 1 is naddest or 1.
So an even length cycle have odd parity -1.
Exactly. Odd length cycles are even permutations. Even length cycles are odd permutations. It's easy to get tangled.
Okay. So odd length cycle means even parity, plus 1.
Now think about the permutations counted by A000246. We just established they only have cycles of odd length.
Right. Every single cycle has odd length.
And we just said every odd length cycle has even parity, signature plus 1.
Ah, so if you decompose a permutation counted by A000246, you only get cycles with parity plus 1.
And the parity of the whole permutation is the product of the parities of its cycles.
So you're just multiplying plus 1 by plus 1 by plus 1, which always gives plus 1.
Precisely. This is a key takeaway from the sources, especially the Wikipedia and Reddit threads you found. Every permutation counted by 000246. Every permutation whose cycles all have odd length must be an even permutation.
Wow. Okay, so the sequence counting odd order permutations, is actually a sequence counting a specific subset of the even permutations. That's not what you'd guess from the name.
It's a beautiful structural consequence, isn't it? The cycle length property directly dictates the overall parity. The name refers only to the lengths.
Okay, that's a great clarification. So we know what we're counting. Permutations with only odd length cycles. Now, how many are there? That's A000246 itself.
Right. The sequence starts 1, 1, 3, 9, 45, 225. Grows quite fast.
Let's quickly check the first few just to make sure this all hangs together.
Oh, yeah.
For N1, S1 only has the identity 1, cycle length 1. That's odd. So count as 1, A000246 matches. For N2, S2 has the identity 1, 2, and the swap 1, 2. Identity has lengths 1 and 1, both odd. Counts. The swap 1, 2 has lengths 2, even. Doesn't count. So just one permutation. A000246 matches again.
Right.
For N3, S3, we have the identity 1, 2, 3, lengths 1, 1, 1, all odd. Counts. We have the 3 cycles, 1, 2, 3, and 1, 3, 2, length 3, odd, both count.
And the transpositions. 1, 2, 1, 3, 2, 3. Each involves an element fixed, so they look like 1, 2, 3, 1, 3, 2, 3, 1.
Oh, right. So their cycle decomposition, so like length 2 and length 1, contains an even length cycle, the two, so they don't count.
Exactly. So for N3, we have the identity plus the 2, 3 cycles. That's 1 plus 2 equals 3 permutations, A000246. It works.
Okay, the definition seems solid. Now, you mentioned connections. The sources point to something quite remarkable, don't they?
They do. The research paper highlights this amazing result. The number of these permutations we've been discussing, the ones with all odd cycle lengths for a given n, is exactly equal to the number of something called ballot permutations of length n.
Ballot permutations. Okay, what are those? Sounds completely different.
It does, doesn't it? The definition is quite different. It relates to sequences and ensuring that prefixes satisfy certain conditions, often related to assents and dissents, like votes in an election where one candidate never trails. The exact definition involves ensuring the height of prefixes stays non-negative.
So one count is based on cycle structure, the other on sequential properties.
Yeah.
And they give the same number.
Exactly the same number.
Yeah.
A000246 counts both sets. This number, let's call it PCN, even has a formula involving double factorials.
Right, the double factorial. N, that's N, N2, N4, down to 1 or 2.
Mm-hmm. The formula for Pn, which is A000246n, is if n is even, it's n1.
And if 1, double factorial squared.
And if n is odd, it's n, n2. You usually define -1 as 1 for this.
Let's quickly test N4. It's even. So 4 down squared equals 3 squared. 3 is 31 is 3, so 3 squared is 9.
And A000246 is indeed 9.
And for N3 odd, so 3 and 3, 3 and 3, 1 equals 3, 1, 1 equals 3.
Which is A000246. The formulas work beautifully. The paper also mentions a recurrence, Pn, Pn1 plus N1 ends to 2, Pn2.
Wow, that equality is pretty stunning. That two such different combinatorial descriptions lead to the same count. The paper you mentioned gives a new proof, too, using some clever decomposition based on where the element lands. That's right, a semi-combinatorial proof that reinforces this link. It's not just a numerical coincidence.
Which suggests there might be something deeper going on than just matching numbers.
Exactly, and that's where the research paper pushes further. It explores whether this connection runs deeper, maybe linking finer statistics of these two types of permutations.
Okay, so not just there are 9 of each type in S4, but maybe something more refined.
Precisely. The paper mentions Spiro's conjecture. This proposes that the equality might hold even when you refine the count. For example, it relates the number of ballot permutations having a certain number of descents.
Descents being where pi plus 1 in the permutation sequence.
Yes, it relates that count to the number of our odd order permutations that have a specific value for something called cyclic weight.
Cyclic weight. Okay, that sounds technical, but the idea is to see if there's a correspondence that respects these finer details. Can we match ballot permutations with calm descents to odd order permutations with, say, cyclic weight k? It suggests a potential bijection, a direct mapping that preserves some structure.
A deeper match. That's fascinating.
And there's another structural property discussed, the Toeplitz property.
Toeplitz. I remember that means matrices where the diagonals are constant.
Exactly. The paper shows that if you construct matrices that count these permutations, both the odd order ones and the ballot ones, based on certain local properties, like the position of the largest element and relative to its neighbors, These matrices turn out to be Toeplitz matrices.
For both types of permutation.
For both. It reveals this unexpected regularity in how the elements are arranged locally. It means the counts based on these local configurations follow the same diagonal patterns for both odd-order permutations and ballot permutations.
So it's not just the total count that matches, but also some measure of their internal local structure shows the same pattern.
Precisely. It's another piece of evidence pointing towards a very deep connection between these objects defined in such different ways, one by cycles, one by sequence properties.
These concepts, Spiro's conjecture, the Toeplitz property, they really show that mathematicians are digging into the why behind that initial numerical equality, looking for the underlying combinatorial reasons.
It really underscores how a sequence in the OEIS, like A000246, can be a gateway to some really rich and complex mathematics.
Absolutely. Okay, let's try to wrap this up. Key takeaways from this deep dive into A000246.
First, the definition. Odd order for this sequence specifically means all disjoint cycle lengths are odd.
Right, not the LCM definition. And second, a surprising consequence. All these permutations are necessarily even permutations, parity plus one.
Third, the remarkable numerical equality. A000246 counts both these odd cycle length permutations and ballot permutations. The formula uses double factorials.
And finally, ongoing research suggests this connection is more than skin deep, hinting at deeper structural similarities, possibly bijections, revealed by things like Spiro's conjecture and the Toeplitz property.
It really emphasizes how fundamental the cycle decomposition is for understanding permutations.
Definitely. It unlocks properties like order and parity, and in this case reveals unexpected connections.
And perhaps a final thought for you to ponder. This striking equality between permutations defined by global cycle properties, all odd lengths, and those defined by sequential rules, ballot conditions, feels like it must have a beautiful combinatorial explanation. A direct mapping, a bijection that translates one structure into the other.
What other hidden bijections might be out there connecting seemingly unrelated permutation statistics or classes? It makes you wonder what other secrets are hiding in the OEIS.
There's always more to discover.
That was our deep dive into OEIS A000246. We hope you found that as fascinating as we did.
Join us next time on The Deep Dive.